Hi students, welcome to the first video on chapter 13, Electrochemistry. Now this is the first of three parts of a video for this entire chapter, and you should have with you the notes for part 1 first so that you can complete the blanks as we go along for this chapter. Now before we go on further, let's just take a quick overview of this chapter so that you have a sense of what to expect. First and foremost, I just want to highlight that in this chapter itself, there is one very big concept, and that is called electrolysis, right? So electrolysis is basically a chemical process whereby we're actually using electricity to actually allow for a chemical reaction to happen, right? So what you see on this screen over here is how to convert from electrical energy to chemical energy. And in electrolysis, there's three very important parts that we need to take note of. One is what we call an electrode, one is what we call an electrolyte, and one is what we call the battery, right? So when it comes to electrode, there are what we call inert electrodes. There are also what we call reactive electrodes. And when it comes to electrolyte, there's what we call the molten ionic compounds, or it can also be the aqueous solution of compounds. And once you know that it's aqueous, it means that it has dissolved in water, so you can either have a concentrated solution or a diluted solution. Within this chapter, you will actually be learning a lot of application in terms of the concept of redox reaction, right? And also to apply on your concept on reactivity series, which are chapters that you have learned this year in Sec 4, right? So we'll go more in depth into what it means by selective discharge in a bit, right? At the same time, you are going to learn two very important industrial applications. One is electrolytic purification, and the other one is electroplating. Last, at the end of this whole chapter, you're going to be introduced to this other concept known as simple cell, which is basically a setup that converts chemical energy to electrical energy, right? And likewise, it taps on your understanding on reactivity series and redox reaction. So why am I giving you this overview before we go on further? I just want to let you know that this chapter depends a lot on the fundamentals of redox reaction as well as reactivity series. So it's good to revise those concepts first before you go deeper into this particular chapter. So let's get started. First and foremost, what exactly is electrolysis, right? So by the end of this part of the video, I hope you will have a better sense of how to define electrolysis and how do you actually use electrolysis as an example or rather an evidence in terms of the structure of ionic compounds in the various different states. First and foremost, what is electrolysis? Now, electrolysis refers to the process of using electricity to break down or to decompose the compound, right? And this is usually an ionic compound in a molten state or in the aqueous solution. And this entire process actually takes place in what we call an electrolytic cell. What you see on the screen over here now on the right is what we call an electrolytic cell, right? An electrolytic cell is basically a setup that allows for electrolysis to happen. If you look at it closely, you realize that, especially for the physics students, you'll be very familiar with this structure here, which is actually the diagram to represent the battery, right? So you have a longer line here, which is a positive terminal, and you have a smaller line here, which is the negative terminal. So this diagram here is showing you that there's actually three batteries connected together in a series manner, right? So there is a battery. Next, there are what we call electrodes. Now, electrodes are these rectangular structures that you see over here. These are solids that allows you to conduct electricity. Then you have an electrolyte, which is the thing that's inside this beaker now. Now, this electrolyte is either a liquid or an aqueous solution, right? So we're going to talk about each of them bit by bit. But before we go on further, let's take a quick look at a video that will help to explain a bit about how electrolysis actually looks like in reality.
If we connect an electrolyzer filled with distilled water to a source of direct current, we can observe a slow evolution of gases. After some time, we notice that the volume of the gas released at the cathode is double that of the gas formed at the anode. To identify the gaseous products of the reaction, we collect each gas in a test tube and check its behavior in the presence of a glowing splint. characteristic cracking sound proves that the gas released at the cathode is hydrogen. The ignition of the glowing splint is evidence that the gas collected from the anode is oxygen, which supports combustion.
Alright, so as you can see from the video itself, right, I'm not so interested in terms of the test for hydrogen oxygen. What I want to show you, if you recall at the start of the video, was that there was this setup that was attached to a battery, and what happened was as electricity passed through the water in this case, there were reactions happening at each of the electrodes, which is that tiny black color solid that you see over there. And how do you know there's a reaction? Because we observe that there's a lot of effervescence, right? Then there are gases that's coming out. Now that itself is electrolysis. Just want to say that even though just now in the video you saw that they are talking about the breakdown of water, right? Okay, eventually you'll learn in this whole chapter that water by itself cannot be a chemical that's broken down through electrolysis. We actually have to add another chemical to it, and that's actually dilute sulfuric acid. Right, we'll talk a bit more about this at the second part of the flip video. Right. So first and foremost, let me just go in depth into what the different parts are. Right. So first and foremost, electrodes. Right. Electrodes are basically the solids that conduct electricity, and they actually connect the battery to the electrolyte. So you see there are two rectangular blocks over there. Those are the electrodes. Right. So these are usually carbon, which is graphite. So if you recall in Sec 3, you learned that graphite is a good conductor of electricity, or it could also be a metal plate. Right. It could be platinum, etc., etc. Now, these are what electrodes are. But now you'll be introduced to two very unique words that it will be the first time that most of you are saying this. One is what we call an anode, and one is what we call a cathode. Now, anode and cathode refers to the different solids they see over here, right? Anode basically refers to the electrode whereby oxidation occurs, whereby cathode refers to the electrode whereby reduction occurs. Now, what I usually teach my students in terms of how to remember anode and cathode, right, is remember these four words: anox, red cat, right? So what it means is that anode is where oxidation happens, cathode is where reduction happens, right? So anox, red cat, right? It's up to you whether you want to use this as a method to remember whether which is the one whereby oxidation or reduction is happening, right? So that it helps you to know what kind of reaction are you looking at. Okay, so there's an anode and there's a cathode over here. Now, don't worry too much about what they mean at this point, because subsequently in the next few slides, I'll go more in depth into what exactly does it mean by oxidation, what exactly does it mean by reduction, what actually is happening over there. Okay, I also want to point out that sometimes during maybe some of you, if you have tuition or if you look at an assessment book, they like to say that, okay, anode is basically the one that is positive, cathode is the one that is negative. Now that is too simple a way to look at what exactly is an anode and what exactly is a cathode, right? So I would rather you remember that anode is where oxidation happens and cathode is where reduction happens, instead of trying to memorize whether it's a plus or is it a minus. Okay, so that's for the electrodes. Now in terms of the battery, right? Battery basically is just an electron pump, right? So in the sense of chemistry, we look at electron flow, whereby electrons move from the negative terminal, they'll move into this electrode here. A reaction will take place. Then the electrons will move back to the positive terminal. So essentially, the electrons kind of move from negative terminal towards the positive terminal. So that's your whole electron flow, right? And in the process, it causes a reaction to happen, the electrolysis reaction. Thirdly, the electrolyte. Now, electrolyte refers to a molten ionic compound or an aqueous solution that is able to conduct electricity. How it does so is that you actually have what we call free moving ions that you learn in Sec 3, right? That act as charge carriers. So some examples of electrolyte will be things like dilute sulfuric acid, molten NaCl, copper 2 sulfate solution. Now, what exactly are the free moving ions? So maybe let me just use molten NaCl as an example. Inside molten NaCl, we have learned in Sec 3 that when an ionic compound is melted, there are your free moving ions. So in this case, there's free moving sodium ions in liquid state because it's molten, and there's free moving chloride ions in liquid state because it's molten. Right? So what happens is that as these ions move around, it actually allows for charge to be carried, and then the whole thing can conduct electricity. Alright, I won't talk too much about the other two here because it's a bit more complicated, and we'll talk about this in the second video itself. But for now, in this video, we are going to zoom in a lot into talking about what happens if there's a molten, that means a liquid form of ionic compound. So knowing about these three parts, how does electrolysis actually works? Now, in the external circuit whereby you have your battery and your wires and your electrode, right? Basically, free moving electrons will flow, right? As they flow from negative terminal to positive terminal using the help of a wire as conductor, right? This one you'll be very familiar with it. Now, but what about inside the electrolyte? How exactly is electricity actually conducted? Now, that's actually done by your free moving ions. So, free moving ions, if you recall, they're actually able to move around, and how they move is that they actually move based on the charge on the electrode. Now, this is a negative charge on the battery. When the wire is connected to this electrode that you see over here, this electrode will also be negatively charged. This is a positive charge of the battery. When this positive terminal is attached to this part of the electrode, this electrode will now be positive. Now what this means is that, remember ions have charge, right? So if you look at the diagram here, you realize that the positive ions, right, where my pointer is pointing at, the positive ions, right, they are all going towards the negative electrode. Why? Because positive and negative attract each other. The negative ions, this that I'm pointing out over here, they will all be attracted to the positive electrode. Why? That's because positive and negative attract each other. Right, so this is actually how the ions actually move around. They look at they will actually detect whether the electrode is a negative one or positive one, and then they will move towards it. And what happens when they move towards it is reaction will take place. What kind of reactions? At the anode, because it is in this case, like what I said, you are attached to a positive terminal, and over here you are attached to the negative terminal. What will happen is that you will attract different kind of ions. Anions will start to move towards here, which is the anode, and when anions move towards them, oxidation happens. So oxidation is basically the losing of electrons, and then a reaction takes place here, and it allows the electron to flow through. At the cathode, which is the negative one that's shown over here, what will happen is that the cations, which are the positive ones, will be attracted to the negative electrode. And when they go over there, they'll gain the electron, that's where reduction happens, and then there's a chemical reaction. So, how does all these things take place? Look at the screen now, and focus on the green color electron. Now, this green color electron represents an electron that comes out from the negative terminal. So, if you follow my laser pointer, the electron will actually move downwards into this electrode here. Right, so this is where the electron is. Now, this means that this electron now is negatively charged. When the cations come over, the cations will encounter this electron and they will gain the electron. So the electron will go to maybe one of the cation, and this will cause a reaction to take place, a reduction reaction to take place. Now, but this electron cannot just disappear. Right? Once it goes to these positive ions, what will happen on this side of the setup is that one of the negative ion, the anion, will sacrifice their electron to go into the electrode. Now, if you follow my laser pointer again, this is now an electron that came out from the anion. It will start to flow back to complete the circuit to a positive terminal. So this is actually how electrolysis allows for electricity to cause a chemical reaction to take place. Right, we'll talk about this in more details as we move on to the second part of this video, where we look at applying it to a molten ionic compound. So having heard about what I've mentioned just now, I just also want to highlight that whenever we say that the cations or anions go through a reaction, we actually say that they are being discharged. Right? So there's this process. Discharge means they lose the charge. That means from cation or anion, they are no longer positive or negative. So no more charge, discharge. So how does electrolysis actually help us to apply this to the concept on ionic compounds in terms of how they conduct electricity, right? So what I'm showing you here, as well as in the notes, right, we're trying to get you to think about what if today, right, the conduction of electricity takes place with a solid ionic compound or with a molten ionic compound or with an aqueous ionic compound, what would be the difference in terms of the conduction? Right? As you can see on this screen itself, you know that the solid one actually doesn't allow for any conduction of electricity, whereas the molten and the aqueous one allows for that to happen. But why is that the case? Okay, so think about this for a second, right? You have actually encountered this before in Sec 3, where we learned about how come ionic substances can conduct electricity in the aqueous or molten state, but not in the solid state, right? So I hope you still remember this. Basically, in the solid states, the ions are held in fixed positions, right? So they are vibrating in fixed positions. They are not free moving. You can't carry charge. You can't conduct electricity. Once you're in the molten state or in the aqueous state, you now have free moving ions. That's where you can conduct electricity. Okay, so I think this is something to be written down within your notes as you compare the different solid, liquid, as well as aqueous ionic compounds. Okay, this is just a recap of your Sec 3 concept. But not everything in the world must be an electrolyte, right? So there are some substances that are actually not able to conduct electricity regardless of the conditions, and we actually call them non-electrolytes. And this is because they do not have any free moving ions. So you see some examples over here. Next, just to quickly consolidate, we have learned about conduction of electricity before in Sec 3. Just want to remind you that when you're looking at electrolyte, because these are actually ionic compounds, right? So this conduction is due to free moving ions, right? When you're looking at metals or you're looking at graphite is basically carbon. You're looking at free moving electrons. So these are very, very different, right? And of course, in this chapter, now that you're learning about electrolysis, right? You know that if you're looking at ionic substance, right, it will actually go through electrolysis, so you'll decompose. But if you're looking at metal or graphite, it's just a normal conduction of electricity, and there should not be any chemical changes. Right, this is also printed in the notes already. Okay, so with that out of the way, that is just an intro to what electrolysis is. Now we are going to get into the application part. Right, so we are going to look at, in this part of the video, in terms of the process of electrolyzing, right, a molten ionic compound. And we're going to use sodium chloride as an example to see what exactly is the reaction that takes place at the anode as well as the cathode. Okay, then hopefully through this example, you have a better sense of why anode is where oxidation happens and why cathode is where reduction happens. And within this part of the video, you will also be understanding more about this concept called ionic equation, or to be more specific, is what we call half equations, right? So this will involve quite a bit of equation writing as well as combining of equation later on, right? As well as we will look at what are the products that might be formed. So just a quick recap as what I've mentioned at the start of the video. In electrolysis, there are two different types of electrodes that might be used. You have your inert ones, which are those that are unreactive. They are not going to participate in the reaction. So usually in our syllabus, we look at things like graphite, which is, like what I mentioned earlier, it's just carbon. Or we have this metal called platinum, it's a type of transition metal. Or you may be using reactive electrodes. So if it's a reactive electrode, it's a bit more complicated. But for now, we'll just focus on the inert electrodes so that we don't care whether the electrodes is taking part in the reaction or not. Okay, so most of the questions that you will encounter are usually inert electrodes. So let's get started with sodium chloride as an example. Sodium chloride is what scientists call a binary compound, whereby it's just a compound that's made out of two elements. Right, so we all know that sodium chloride means it's made out of sodium and chlorine. So two different things only. Right. So in sodium chloride, when it has melted, right, because it's an ionic compound, then there will be a free moving sodium ion and your free moving chloride ions. Right. So these are standard stuff that we've been talking about so far. So how will this look like in terms of the setup? Right. This is how the setup will look like, whereby you will have molten NaCl that's being heated up until it melts, right? So you have your Na plus and Cl minus inside this electrolyte. So remember that this whole thing is an electrolyte. Then you have your electrode that's attached to the wire as well as the terminal, right? So because you have attached in this manner, we also know that this electrode will now be negatively charged, while this electrode will now be positively charged, right? And what this means is that, remember just now I mentioned that in the molten ionic sodium chloride, there will be Na plus and there will be Cl minus. These two are the ions that are free moving. So they'll be moving within the electrolyte, right? Depending on the electrodes that they encounter. So there's a Na plus which is positive, and there's a Cl minus which is negative. And if you look at this drawing over here on the left hand side, you know that one of the electrodes is actually positive, one of the electrodes is actually negative. So inside the entire electrolyte, what will happen is that the chloride will actually move towards the positive electrode. Why? Because negative and positive attract each other. So the negative ions, which is the anions over here, will start to be attracted towards the positive electrode that you see over there. Right. So what do the negative ions do over there? Now the anions will actually go through oxidation. As what I said just now, an ox red cat. Right. So anode is where oxidation happens, and cathode is where reduction happens. So what happens over there is that the anion will actually lose electron, and when they lose electron, they will actually form chlorine gas, and that's where oxidation happens. Right. So to represent this chemical reaction, we use what we call a half equation. A half equation is represented over here, whereby you have two chloride reacting, and then it forms a gas which is chlorine gas. Right. If you look at this equation over here, what is important is to realize that you have an ion which is Cl minus, and you need to form the product of chlorine gas because it's group 17 is Cl2. Right. So if it's Cl2, you know that you need two sets of the chloride. That's where when you balance the whole thing, you will have a 2 over here, right? So that is how the equation is being constructed. Secondly, you realize that in this equation, it's a bit interesting that they have these two electrons on the right hand side. Remember, over here is about losing electrons. So how do you go from chloride to chlorine by the loss of electron is that you need to lose two of the electrons, because each of the chloride has a negative charge here. The two negative charge will come out. When it comes out, it becomes that two electron that you see over here, and then you form your chlorine gas. Right. So this part will take a while to get used to, because you're not you don't always construct such ionic equations, right? Usually you construct an ionic equation when we gave you a chemical equation at the start, right? But over here, you need to really understand that because you are starting with just chloride ions, but you want to form chlorine gas. So as a whole, we say that chloride ions are being discharged to form chlorine. Right? So this is what happens at the anode. This is a form of oxidation, because anode is where oxidation happens. Now, what about at the other electrode? At the other electrode, you recall that there's still your sodium ions, right? The other electrode is where you have your negative charge, right? So just now is where you have a positive charge. So this time round, what you'll notice is that the sodium ion, which is the Na plus, will now be attracted to a negatively charged electrode, right? So when they're attracted over there, the cation ions, the sodium ions, will actually gain electron to form sodium metal, right? And this is actually a form of what we call reduction. And if you look at the half equation that's shown over here, the sodium ion, Na plus, it actually gains one electron to form sodium metal, which is Na over here. Now this equation, there's no need for you to put a number 2, because sodium as a metal, the formula is just Na, right? Not like chlorine just now when it's group 17, it's actually diatomic, so you have a Cl2. So you just need to gain one electron because it's a positive charge, therefore it's just plus a E minus, right? So from now onwards, for this entire chapter, you need to get familiar to use this thing that we call half equation to show the kind of reaction that's happening at the cathode as well as the anode. So in terms of a sentence, we'll just say that this means that sodium ions are being discharged to form sodium. You may also notice that this sodium over here is indicated as a liquid state. Now, why is that the case is because the setup is very, very hot, right? Because to get molten sodium chloride at the start, right, you actually have to heat up the entire thing until maybe 600 or 800 degrees Celsius. That means if you were to form any form of solid metal, right, chances are the metal will melt. Right, so because the setup is very hot, this thing will have already melted also. That's why the state over here is written as a liquid form. Okay, so in summary, when we bring both together, right, what it means is that at the anode, actually there's a reaction that's shown over here, whereby the chloride ions are being oxidized to form chlorine. Okay, remember that NOx. And then at the cathode, you actually have a reduction whereby the sodium ion is being reduced to form sodium metal, right? That's your reduction and cathode. Okay, so now after knowing about these things, right, we are going to actually construct what we call an overall equation. Now to write the overall equation, right, it can be a bit tricky over here. So I just want to highlight a few steps that you need to take note of first. Okay, first and foremost, in order for you to write an overall equation, you must always remember to make sure that the number of electrons in the two equations are the same. So if you look at these two equations that you see over here, right, you have one at the top whereby there's two electrons formed. You have one at the bottom whereby there's only one electron used over here. You need to start first by making sure that they have the same number of electrons. So how do you do that is to make sure that for the one at the bottom, you actually multiply the entire equation by a 2. And then this will form an equation that is shown over here, whereby there's 2 Na plus with 2 electrons and 2 Na. Right, so this will then allow the electrons to actually match the one at the top. Then, to close the two equations together to form an overall equation, you will actually take all the reactants and add them together on the left hand side. So this will give me 2 chloride from the top, 2 sodium from the bottom, plus the 2 electron from the bottom. Now this will be how the left hand side will look like. Basically, you take all the reactants together. After you have confirmed that the electrons are the same, you bring them all together. Then on the right hand side, just bring all the products down. So you have your chlorine, your 2 electrons, and then you have your 2 of the sodium over here. Okay, so once you have done with this step, right, you can start to look at whether things are being repeated on the left and right side, and then you can cancel them off. So for example, there's 2 electrons here, and there's 2 electrons here. You can just strike them out. And now, that's where you combine the necessary chemicals, and that's where you'll get your overall equation. So these 2 Cl- and 2 Na+, right, actually just represent a molten sodium chloride, because we know that they are just the free moving ions. And then the product over here, you will have your chlorine as a gas, and then you have your 2 Na as a liquid. So this is actually how the overall equation looks like. And if you look at it closely, you realize that it's essentially telling you that the NaCl has been broken down to form chlorine and sodium. And that is the meaning of electrolysis, using electricity to break down a compound into the different products that you see over here. Okay, so just to sum up, the overall reaction will be represented by this equation over here, whereby 2 NaCl is actually broken down to form 2 Na plus Cl2. And how do we construct this entire thing is, as mentioned just now, you have to first balance the number of electrons, then combine the reactants together, combine the products together, and cancel out those that are being repeated on both sides. Okay, so with that, this will be the last part in terms of the lesson on part 1 of the notes. We'll move on to the self-practice questions in the worksheet, where you might want to pause the video first, because the next part will just be going through the answers on the self-practice portion. Okay, so before we zoom into the self-practice question, I thought it would be good to just show you all how we actually make use of the notes to record down the various things that was being shown just now on the slides. Right, so this is actually on page 4, and this is how I will actually present my own understanding of electrolysis, so that subsequently when you see the same diagram, right, at least you understand how it works. So when you look at a question like this, right, whereby you're focusing on molten sodium chloride, you always start first by looking at what are the type of ions that are present. So you have your anions, which is chloride, and you have your cation, which is Na+. Then as a student, when you are doing the question, right, do take note of that if you are attached to a negative terminal, and if you are attached to a positive terminal, it will mean that the electrode will have a certain polarity, right, a negative or positive. And then, because of the ions that you have inside the whole solution, you should know that there is your chloride ions, and there's also your sodium ions, right? These are all free moving ions now. So free moving will mean that they will actually move towards the electrode that they have attraction towards, right? And then this will happen, and that's why at this particular electrode over here, we see a reaction involving sodium. And then at this particular electrode over here, we see a reaction involving chloride. So you must always start first by understanding what kind of ions you have, what's the charge of the electrode, which ion went to where, then you can think about the kind of reaction that will happen. Okay, so cations and cathode, so I think this one should be quite straightforward. Anions with your anode, so that's how the reaction takes place. So now let's take a look at the self-practice question. Now the self-practice question here, right, for question 1, is actually trying to get you to rethink about your understanding of the electrical conductivity of different chemicals. Now in terms of the solid state, when it comes to conduction of electricity, in our syllabus, we only learn that in terms of conduction in the solid state, you either look at just metals, that means just the pure metal, in this case copper. The other options that you'll have in your notes will be graphite. Only these two would be the ones that can conduct at the solid state. In terms of conduction in the liquid state, right, definitely the thing that you will come to your mind is should be your ionic substance. But do not forget that you also have your pure metals. Because pure metals, so long as they are metals, they are able to conduct electricity because they are free moving electrons, right? That's why your copper will appear here again. Right, so this is something to take note of, right? So I think generally, if it's a solid state, it's quite clear cut. There's either metal or graphite. Generally, if it's a molten state, liquid state, it's also quite clear cut. It's either ionic or you're just looking at metals. Now, but when it comes to aqueous, right, I agree that it gets a bit confusing. Based on what I've shared in the video just now, you'll know that ionic compounds must be able to have free moving ions because they will dissolve. But now you see this hydrogen chloride. This is kind of weird, isn't it? And that's because hydrogen chloride, in terms of formula, is actually HCl. Now HCl, if you recall in Sec 3, it is actually something that can dissociate in water to form H plus and Cl minus, which is your hydrochloric acid, right? So hydrogen chloride, if you add it with water, it will actually give you ions. This is a very unique case, but it's also something that is interesting to take note of, right? But then other than that, the non-electrolytes is as per what I mentioned just now, right? Usually your non-metals like sulfur, covalent substances like sugar, organic compounds like ethanol. Okay, so I think this is a good recap, I would say, right? And also to remind yourself about the more unique kind of situation. Question 2 is really just to get you to think through about the ions, right? So we have went through just now that these are all ionic compounds, and in the molten state, it's just basically looking at the kind of ions that's inside. So you have zinc, you have chloride, etc., etc. And the right hand column here is getting you to recap about how will the ions move. So one easy way to take note of is that in this whole diagram that I said just now, in case you can't remember about your anode as well as your cathode, what you can do is actually to just draw it out first to have a simple diagram for yourself. And you can see over here is that there is a negative and positive terminal, whereby this will be negatively charged and this will be positively charged because of what they are attached to, right? And what comes to the electrode that's negatively charged over here, it must be your positive ions will come here. What comes to the electrode that's positively charged, it must be your negative ions. So that's actually a good way for you to understand about whether it's moving towards which of the electrode, right? Then in terms of whether is it anode or cathode that you're looking at, just want to remind you that anode is where your oxidation happens, and cathode is where your reduction happens. And for those of you who are more familiar, you'll know that actually it must be negative ions over here because only negative ions can be oxidized, right? Those of you who are a bit more familiar, like what I said just now, you'll notice that only the positive ions can come over here because only positive ions can be reduced, right? So that's actually how some students will start to realize, hey, there's actually a certain kind of pattern per se, right? So in terms of the ions and where they go, right? So this will cover on question 1 and question 2, but don't worry, we'll talk more about this thing when we meet face to face. Question 3 is something that I want to start from scratch to show you how I will analyze this whole thing. So this question is asking about molten lead-2 chloride, right? So this is an ionic compound. In molten lead-2 chloride, the ions that should be inside, the anion will be chloride ions, and the cations will be lead-2 ions. In this whole setup, there's an electrode. So there's an electrolytic setup. So this will be negatively charged, and this will be positively charged. So now we ask ourselves, which is the ion that goes towards the negative one? which is the ions that go towards the positive one, right? Remember that inside, they are all free moving. So you have your lead, you also have your chloride ions. Okay, and based on what we learned just now, the chloride being negatively charged will move towards the positive electrode. The lead 2 being positively charged will move towards the negative electrode. And then at their respective electrode, reaction will start to happen. What's the reaction that can happen? We ask ourselves, lead 2, what can it become? It must become lead, right? So this is actually what? A reduction or an oxidation? Ask yourself, think about it. On the other side, chloride can become what? It must become Cl2, right? So is this reduction or is it oxidation? Ask yourself, think about the charges and whatnot, and recap a bit about whether it's reduction or oxidation. And then I think most of you will realize that this is actually a form of oxidation, whereas this is a form of reduction, right? And that's actually how we can then realize that, hey, this must be the cathode and this must be the anode, because an ox red cat. So that's actually how most students go about deriving the cathode and anode as well as the reaction. You start off first by knowing where the ions go. Then you ask yourself, what will this ion react to become, right? It is usually, it just becomes the element. So you realize that if it's lead 2 plus, then it must be reduced. But because chloride is a negative charge, to become the element, it's actually a form of oxidation. Okay, so for part A, please answer yourself. I'll focus on part B in terms of the electrode, right? So at the anode, where the chloride ions that we have identified, what will happen is that the chloride will actually try to become Cl2. So of course they are liquid state and this is a gas state. But once you look at this, you know that the equation is not balanced. That's why there must be 2 chloride ions to form your Cl2 gas. But this is about oxidation, right? So there must be a loss of electron. How many electrons should come out? There should be 2 of the electron, because it's 2 of negative charge. Therefore, there should be 2 electrons coming out. So that's what is happening at the anode. And this, like what I said earlier, an ox red cat, this is a type of oxidation. Okay. Next, at the cathode. At the cathode, as I've mentioned, we know that there's Pb2 plus in the molten state. It wants to become Pb. Most likely it will be molten because it's very, very hot, like I said just now. So what is required for the reaction to happen? This must be a type of reduction. So electrons must be gained. How many? And you realize that it's actually 2e minus. Why? Because this is a 2 plus. You need 2e minus to give it a neutral. So then this will actually be an example of a reduction. Alright, so these are what I call half equations. We represent what happens at each of the electrode, right? And we have the electrons inside. Now, to construct the overall equation. Now, overall equation, if you recall, important thing is to make sure that the electron must match. In this case, it matches. So once it matches, what we can do is we combine all the reactants together. So 2Cl minus plus lead 2 plus 2E minus. So these are all the reactants. Products wise, chlorine gas plus 2E minus plus lead liquid. Right? Then now we start to cancel things that's being repeated. So the electrons are being cancelled, and you look at the remaining things, you realize that, hey, this is actually your PbCl2, lead 2 chloride in liquid form, and in the electrolysis, it actually forms chlorine gas plus lead as a liquid metal. So in this whole answer here, this is the overall equation for what happened. The lead 2 chloride was decomposed to form chlorine and form lead, hence electrolysis. Okay, so I hope that as we go through this entire chapter, when you go to part 2, part 3, right, whenever you see a diagram that looks like this, try to start off first by writing down the ions. Think about where the ions go. Think about the type of reactions. Go and construct a half equation, then construct your overall equation. Generally, for electrolysis, these are the steps that's required. Okay, as for question 4, I would like you to take some time to fill this in yourself, and we'll go through this together in class.